Right now, the most powerful computer on Earth is calculating something. It's been running for 3 years. The answer? It won't finish for another 47 million years. As we enter 2026, that limit is finally being challenged. IBM and AMD have crossed a critical threshold, moving quantum supercomputing from theory into working reality. This isn't just an upgrade, it's a Sputnik moment. One policymakers in Washington have been watching for, and one that exposes how extraordinarily difficult this technology is to replicate, even for rivals like Beijing. On August 26, 2025, that shift became real. IBM and AMD didn't just announce a partnership, they outlined a concrete blueprint for what IBM calls Quantum-Centric Supercomputing. It's a hybrid architecture designed to bridge two computing worlds that were once thought to be a decade apart. Then, in October 2025, they demonstrated a critical milestone, running real-time quantum error correction decoding on standard AMD hardware. Not custom control systems, commercial-grade silicon, and it performed roughly an order of magnitude faster than required. That effectively moved the program about a year ahead of schedule. Here's why that matters. For the first time, IBM's published roadmap points to a concrete window, 2026, for demonstrating quantum advantage, solving a real scientific problem that classical supercomputers cannot realistically finish. This isn't speculation anymore, it's an engineering timeline. For the next 15 minutes, I'm going to break down what this hybrid machine actually looks like, why this computing model is extraordinarily difficult to replicate, including for rivals like Beijing, and what problems humanity may finally be able to tackle because of it. Let's dive in. Okay, first we need to understand the wall, and I mean a real wall, not a marketing metaphor. For roughly 60 years, computing followed a simple rule. More transistors meant more power. Moore's law. Every 2 years, performance doubled, and for decades, it worked spectacularly. The phone in your pocket now outperforms the supercomputers that sent humans to the moon. But here's the part that rarely gets advertised. For years now, we've been running into entire classes of problems that even the most powerful supercomputers on Earth cannot realistically solve. And I don't mean slow, I mean computationally intractable. Let me show you what that actually means. Consider optimization at scale. Imagine a delivery driver who needs to visit 50 cities and return home. The question sounds simple. What's the fastest possible route? The problem is that with every additional city, the number of possible routes doesn't grow linearly. It explodes. By the time you reach just a few dozen cities, the number of possible paths becomes astronomically large, numbers with dozens of zeros. Even if the fastest supercomputer on Earth checked routes non-stop, it would take far longer than human civilization has existed to guarantee the perfect solution. This is why companies like Amazon don't solve these problems exactly. They rely on approximations, solutions that are good enough, not perfect, because perfect is computationally out of reach. Now consider medicine. When researchers design a new drug, they're trying to predict how a molecule will interact with proteins in the human body. That interaction is governed by quantum mechanics, electrons, energy levels, probability amplitudes. Even a relatively small molecule involves interactions between dozens of atoms. To model those interactions exactly would require tracking an explosion of quantum states that quickly exceeds what classical computers can handle. This is a major reason why drug development takes over a decade and costs billions of dollars, not because scientists are slow, but because the underlying calculations become computationally infeasible with classical methods. The same problem appears in climate science. We're not short on data, we're overwhelmed by it. What limits us is the ability to simulate the quantum-level chemistry happening inside the atmosphere, reactions between molecules that cascade across massive systems. Modeling those interactions precisely pushes classical computers beyond their practical limits. Here's the core issue. Classical computers think in bits, ones and zeros, on or off, true or false. That framework is incredibly powerful for many tasks, rendering graphics, running AI models, managing global networks. But for problems rooted in quantum physics, which is most of the physical universe, it's a poor fit. Trying to force those problems into classical computation is like trying to paint the Mona Lisa with a sledgehammer. The tool isn't wrong, it's just the wrong tool for the job. This is what scientists call intractable problems, and there are thousands of them blocking progress in medicine, materials science, energy, artificial intelligence, and climate research. So, how do you break through that wall? You don't throw away classical computing. You build a new tool to work alongside it, and then engineer a way for both tools to work together. And that is exactly what IBM and AMD have just done. All right, this is where the real engineering nightmare begins. We all know quantum computers are powerful. We've heard about superposition, the idea that qubits can explore many possible solutions at once. But here's the catch that kept quantum computing trapped in the lab for more than 30 years. Qubits are extraordinarily fragile. They're effectively allergic to the universe itself. A tiny vibration, a small temperature fluctuation, or a stray electromagnetic field can cause a qubit to decohere, losing its quantum state in microseconds. To make a quantum computer actually work, you have to detect errors and correct them faster than the qubits decay. It's a continuous race against the clock. And for years, this was the bottleneck. The control systems responsible for detecting and correcting those errors were external. They sat too far away from the quantum processor, and they operated too slowly. By the time a correction was calculated and sent back, the qubit had already lost its state. That's the problem IBM and AMD just broke through. In October 2025, they didn't just demonstrate error correction, they demonstrated real-time quantum error correction decoding at the hardware level. They moved the brain of the system right next to the heart. Using a standard AMD FPGA, commercial reconfigurable silicon, they decoded quantum errors with microsecond scale latency, fast enough to keep pace with the quantum processor itself. Think of it this way. The quantum processor is a brilliant but fragile mind, generating ideas at the edge of what physics allows. The AMD chip is the hyper-fast translator standing right beside it, catching mistakes and correcting them before the system even notices. Crucially, this decoding ran roughly an order of magnitude faster than required to maintain stability. That changes everything. It means the primary engineering bottleneck holding quantum systems back has been removed. We're no longer waiting on exotic new physics. We're now in the realm of scaling, integration, and manufacturing. And that leads to the geopolitical reality. This solution depends on high-performance FPGAs, ultra-low latency integration, and deep co-design between hardware, software, and quantum systems, all across a tightly coupled ecosystem. That kind of end-to-end integration is extraordinarily difficult to replicate in isolation, particularly in environments like Beijing, where access to advanced programmable hardware and cross-stack collaboration is constrained. So they built the machine. The real question is what a quantum-centric supercomputer actually enables. The answer isn't abstract theory or futuristic demos. It's a shift in which problems move from being computationally unreachable to becoming engineering challenges that can finally be tackled directly. One of the clearest examples is medicine. Today, discovering a new drug typically takes more than a decade and costs billions of dollars. Not because scientists are guessing blindly, but because classical computers struggle to accurately model the quantum interactions that determine how molecules behave inside the human body. IBM, working with the Cleveland Clinic, is already using hybrid quantum systems to build high-fidelity simulations of proteins and molecular interactions, often described as digital twins at the quantum level. Instead of synthesizing and testing vast numbers of compounds through trial and error, researchers can computationally evaluate how a candidate drug binds to a target, how stable that interaction is, and which side effects are most likely before anything is manufactured. This doesn't eliminate experimentation, but it dramatically narrows the search space, with the potential to reduce years of trial and error in areas like cancer, neurodegenerative disease, and rare disorders. The same shift is beginning to appear in materials science. Addressing climate and energy challenges ultimately comes down to materials. better batteries, more efficient catalysts, and entirely new classes of superconducting compounds. These systems are governed by quantum mechanics, and classical simulations struggle to capture their full behavior. Hybrid quantum supercomputing allows researchers to explore atomic-scale material properties with far greater accuracy, making it possible to systematically search for new material configurations. That turns materials discovery from educated guessing into a computational design problem. It doesn't guarantee breakthroughs overnight, but it opens regions of material space that were previously inaccessible to simulation. Artificial intelligence is another area where the impact is less about replacing existing systems and more about removing bottlenecks. Modern AI is powerful, but it is also expensive. Training large models consumes enormous computational resources and energy because optimization becomes increasingly difficult as systems scale. Quantum systems don't replace classical AI. Instead, they assist with specific optimization and sampling tasks, the mathematical cores that slow training and limit efficiency. In practical terms, this could mean faster convergence, better exploration of solution spaces, and lower energy costs for training advanced models. Improvements that cascade into other fields like drug discovery and materials research. Finally, there is optimization at global scale. Modern logistics, finance, and infrastructure all reduced to massive optimization problems layered on top of one another. Companies like FedEx route millions of packages every day. Airlines schedule fleets across continents. Energy grids balance supply and demand under constant constraints. As these systems scale, their complexity grows exponentially. Classical computers rely on approximations. Quantum algorithms offer new ways to explore these solution spaces more efficiently. Even incremental improvements at this scale translate into massive reductions in cost, waste, and inefficiency across the global economy. All of this leads to the moment that ties everything together. According to IBM's published roadmap, 2026 represents the first realistic window for demonstrating quantum advantage, a real scientific or industrial problem solved better, faster, or more efficiently than any classical supercomputer could manage alone. Not a lab demo, not a toy problem, a practical breakthrough. This isn't a promise or a marketing slogan, it's an engineering target on the calendar for this year. So let's address the obvious question. Does this mean quantum computers are about to replace your laptop? Short answer, no. The future of computing isn't quantum replacing classical, it's quantum alongside classical. We're moving toward a hybrid architecture where different processors handle the tasks they're best suited for. Your CPU manages general-purpose logic. Your GPU accelerates graphics and large-scale parallel workloads. And now, the QPU, the quantum processing unit, joins the stack as a hyper-specialized accelerator for problems that were previously computationally unreachable. This is the model IBM and AMD are cementing. By 2026, the goal isn't just to build larger quantum chips, but to make QPUs a dependable component of the data center environment, integrated, orchestrated, and usable alongside existing infrastructure. That's where IBM's Nighthawk processor comes in. Each module contains 120 qubits, and IBM plans to link 3 of them into a single 360-qubit system. That number matters because it marks the transition from isolated physics experiments to workloads that begin to resemble industrial computation, systems stable enough to run meaningful algorithms for extended periods. What makes this transition especially significant is how it's being built. IBM and AMD aren't creating a closed proprietary system. They're deliberately pushing an open, standardized approach, using commercial AMD FPGAs and open-source software frameworks like Qiskit to orchestrate hybrid workloads. That openness isn't accidental, it's strategic. By establishing a common architecture and software foundation early, they shape how researchers and developers write the next generation of hybrid applications. As that ecosystem grows, the hardware, tools, and workflows become deeply interdependent, creating momentum that's difficult to replicate from scratch. This isn't unique to IBM and AMD. NVIDIA, Google, and others are pursuing similar heterogeneous strategies. What's emerging is a Western-led computing stack where CPUs, GPUs, and QPUs work together, open to partners, but reliant on tight integration across hardware, software, and manufacturing. In that environment, leadership isn't just about having the best chip. It's about setting the standards, building the ecosystem, and gaining years of operational experience before competitors can catch up, including rivals operating under more constrained conditions, such as in Beijing. IBM and AMD didn't just arrive early. They helped define how this future will function. We are living through a genuine turning point. For decades, quantum computing was always described as being 10 years away, always theoretical, always just out of reach. But the milestones we've discussed today, August, October, and the roadmap into 2026, aren't projections anymore. They are engineering realities. The wall is beginning to crack. Problems that once sat beyond the limits of computation, from complex disease mechanisms to large-scale climate modeling, are starting to move out of the realm of theory and into the realm of the solvable. But it's important to understand the broader context. This isn't only a scientific transition, it's an infrastructural one. Whoever builds the platforms, standards, and ecosystems behind these systems ultimately shapes how the next century of computation operates. Right now, IBM and AMD aren't just building machines. They're shaping an ecosystem, defining the tools, workflows, and software foundations developers will use to write the next generation of applications. That early momentum matters because ecosystems compound. So here's the question worth asking. Is an open, standards-based ecosystem enough to preserve long-term leadership? Or will a state-driven, vertically integrated approach, like the one emerging in Beijing, eventually find alternative paths around today's constraints? I'd genuinely like to hear your perspective. Let me know what you think in the comments. And if you want to understand the next phase of this competition, why approaches like photonics, advanced packaging, and alternative compute architectures could reshape the balance, make sure you're subscribed. The future isn't coming. It's being built piece by piece right now. Thanks for watching. And if this blew your mind even half as much as it blew mine, smash that subscribe button and hit the bell, because this technology is moving fast, and we're going to be covering every breakthrough as it happens. The future isn't coming. It's already here. Thanks for watching.